Imagine you find a short movie script detailing a scene between a person and their AI assistant. The script includes the person's questions, but the AI's responses have been torn off. If you had a machine capable of reading the remaining text and making a sensible guess about the very next word, you could feed the script into it, predict the first word of the AI's answer, add it to the page, and repeat the process to finish the dialogue. When you interact with a chatbot, this exact process is happening behind the screen. This diagram illustrates what the machine is actually doing. A large language model is a deterministic mathematical function. It does not think of a single word with absolute certainty. Instead, it reads the input text and outputs a probability distribution, assigning a specific mathematical likelihood to every possible next word in its vocabulary. But if the math is completely deterministic, why do you get a different answer every time you ask a chatbot the same question? The trick is that the model is programmed to occasionally select a less likely word at random, rather than always picking the highest probability. Rolling the dice on those slightly lower probabilities breaks the rigid math and creates text that flows well. The conversational responses feel natural because they are mathematically sampled from weighted probabilities rather than recited as absolute certainties. To make those probability predictions accurate, models learn by processing text pulled from the internet. The volume of data is difficult to picture. If a human tried to read the baseline dataset used to train a model like GPT-3, reading nonstop 24 hours a day, it would take them over 2,600 years. This diagram represents the internal mechanics of a large language model. The behavior is dictated by continuous mathematical values called parameters or weights. You can think of them as hundreds of billions of dials. No human deliberately sets them. They begin at random, meaning the early model only outputs complete gibberish. To fix the gibberish, the model undergoes pre-training. An algorithm called backpropagation passes over the dials. It takes a training example, holds back the final word, makes a prediction, and compares it to the true last word. The algorithm then tweaks all the dials to make the model slightly more likely to guess the true word next time. This adjustment happens across trillions of examples. If you could perform 1 billion additions and multiplications every single second, completing the operations to train a large model would take well over 100 million years. Repeating this across trillions of examples transforms a random text generator into a precise pattern recognizer. But pre-training has a strict limitation. The goal of accurately auto-completing random passages from the internet is different from the goal of being a polite and helpful assistant. To bridge this gap, chatbots undergo a secondary phase called reinforcement learning with human feedback. This diagram shows how this secondary phase works. Human workers review the model's text and flag problematic or unhelpful predictions. These corrections act as a new signal, triggering further mathematical adjustments across the dials to ensure the highest probability outputs align with human preferences. Raw data scale creates the model's capacity for language, while human feedback provides the alignment required for a practical assistant. Older language models were slow because they processed text strictly one word at a time. Modern models rely on special chips called GPUs and a 2017 architectural design known as the transformer, which allows them to process vast amounts of context in parallel. This animation shows the first step inside a transformer. Because the training math only works with continuous values, the model drops entire sentences in simultaneously and translates the linguistic words into vertical lists of numbers, known as vectors. If the word bank always translates into the exact same list of numbers, how does the math distinguish between the bank of a river and a financial institution? The solution is a mechanism called attention. The transformer allows the lists of numbers to communicate with each other in parallel. By looking at the surrounding context, the numbers for river push data into the numbers for bank, physically shifting their values to encode a more specific meaning. From there, these context-enriched numbers flow through a feed-forward neural network. This operation gives the model extra capacity to apply the broader patterns of language it memorized during training. Inside a large language model, meaning is not established by hard-coded grammar rules. It is a fluid, mathematical relationship between surrounding words, all calculated simultaneously. While human engineers design the architecture of transformers and attention, they do not program the specific answers. The final output is an emergent phenomenon resulting from the tuning of those hundreds of billions of parameters. This cascading sequence illustrates the complete pipeline. Raw text drops in and transforms to number lists. Lines of attention connect and refine them. The data passes through a web of feed-forward networks, and it all outputs into a final probability bar chart. Pushing these billions of simple math operations through optimized hardware produces the fluent, useful AI we interact with today.